faithfully delivering value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, the book we're interpreting for you is The Scale of the Universe. The subtitle of this book is From the Infinitely Large to the Infinitely Small. The author, David Blattner, is a fascinating person. His main job is actually as a digital publishing expert, and he's really skilled with design software like Photoshop and typesetting tools. He's also written quite a few popular science books, which have been translated into over 10 languages and sold hundreds of thousands of copies globally. But, as a technology expert, not a professional scientist, David has a unique perspective in his popular science works. He excels at starting from everyday objects and leading readers into new realms. Oh, whoa. You'll soon grasp this from The Scale of the Universe. Before introducing the book, let's hear a story. In the classic sci-fi work, The Hitchhiker's Guide to the Galaxy, it tells of a massive alien fleet coming to attack Earth, only to realize they messed up the scale.
So, this grand army lands in a park and gets eaten by a little dog.
This story shows that scale is super important when you're trying to understand the world. The scale of the universe. This book starts from the most common spectrums in daily life, immersing us in the universe at different scales. Before talking about scale, we first introduce the concept of human scale. The so-called human scale refers to the range where humans feel comfortable, also called the middle world. In life, we always tend to base our perception of reality on the human scale. This scale includes distances we can walk easily, times not exceeding the average human lifespan, and temperature ranges on Earth from icy cold to fiery heat. We know that humans only perceive a tiny part of the world. The real thing is way more vast, but emotionally, humans stay stuck in this middle world, struggling to grasp things beyond their senses. However, to truly see humanity's place in the cosmos, we must step out of our comfort zone and explore the unknown. The scale of the universe covers different scales for 6 spectrums: numbers, size, light, sound, heat, and time, helping us experience what's beyond human scale. Now, let's start with the first spectrum, numbers. We're great at handling everyday numbers, like checking the time, grocery shopping, or doing accounts, but none of us can escape our human limitations. Number 3, big numbers are our weak spot. In this spectrum of numbers, how big is the human scale range? Imagine this. If there are 3 apples on the table, you can count them at a glance. But if the apples increase to over 20, you'll need to count them carefully. Then, what about a basket of apples, a cartload of apples, or even a whole swimming pool filled with apples? You'll soon get confused and can't even tell if that huge pile has hundreds, thousands, or tens of thousands. For humans, the upper limit for intuitively perceiving numbers is only a few dozen. Once the number of objects exceeds 100, you start estimating approximations or using known numbers as references for larger ones. We can understand it rationally, but we can't form a concrete concept in our minds. For example, if you're given 10,000 apples, you know what a big pile that is. But if you swap apples for cash, you instantly know that 10,000 yuan is just 100 yuan bills, a small stack. However, when it comes to money, our understanding seems to expand quite a bit. But note, your understanding of money, based on new references like a new smartphone or a big screen TV, still has an upper limit, which depends on your own income and assets. So how can we grasp large numbers? A simple trick is to compress it to our familiar scale. Take money as an example. Suppose an average person earns 50,000 a year and a rich person earns 5 million. What's the difference in their lives? When using your imagination, don't divide your own income by 100. Instead, divide the price of everything by 100. A new laptop would cost just 40 yuan, and a new car only a few thousand. As long as you're rich enough, everything seems cheap. To understand Jack Ma's wealth, don't think about his 30 billion fortune. That's just a meaningless large number. Well, You just need to imagine that the price of everything becomes 1 millionth of its actual price. The latest iPhone would cost just one fen, a supercar about a few yuan, and a mansion worth 50 million in your eyes would only be worth 51 to him. For ordinary people, wealth of 300 billion is completely beyond imagination. But shift your gaze beyond wealth. 300 billion might not seem like much at all. Your body contains about 100 trillion cells, which is equivalent to 10 to the 14th power. Look even further. The radius of the solar system is only about 1,000th of a light year. And currently, the observable universe has a radius of about 46.5 billion light years, with approximately 16 times 10 to the 21st stars within it, which seems unbelievably huge. But actually, it's equivalent to the number of molecules in 10 drops of water. So how big is the largest number? In 1938, American mathematician Edward Kasner asked his 9-year-old nephew, Milton, to name an incredibly large, unimaginable number. The child answered, calling it a Google, and defined it as 10 to the 100th power, which means writing 1 followed by 100 zeros. This number surpasses the limits of known things. There's nothing in the real world that reaches the scale of a Google. All atoms in the known universe total only about 10 to the 81st, which is 19 orders of magnitude smaller than a Google. Therefore, larger numbers belong solely to the realm of pure mathematics. On the other end of the number spectrum, negative and imaginary numbers are also concepts that belong only to pure mathematics. You can't count -3 apples, and your phone's calculator doesn't have imaginary numbers. Similarly, infinity belongs only to pure mathematics. Math has a basic premise that infinitely large and infinitely small things exist in the world. But infinity isn't an endpoint. It's more like an idea. We can't precisely point out where extremely large numbers become equivalent to infinity. No matter how large a number you think of, infinity is always larger. The distance between a Google and infinity isn't closer than between 1 and infinity. Infinity plus 1 equals infinity, and infinity plus infinity also equals infinity. You might naturally think that the number of odd numbers is half of the natural numbers, but that's not true. Now, the number of odd numbers, even numbers, and natural numbers are all infinite. Negative numbers, imaginary numbers, and infinity. These abstract concepts, existing only in theory, help us build the magnificent edifice of mathematics. Scientists can calculate rocket trajectories and quantum movements, leading humanity to fly to more distant places. Having covered the first spectrum, numbers, next we introduce the second spectrum, size, which is easy to measure within the human scale, roughly from a few millimeters to a few kilometers. When facing objects over 1 or 2 kilometers, we quickly lose our perception of size. You might see it, believe it exists, but you can't fit it into the human scale. Interestingly, our perception range for length is much larger than for height. Take a simple example. When we talk about space, everyone thinks it's very far away. But actually, the height of the International Space Station from Earth's surface is about 370 kilometers, only slightly farther than the distance from Nanjing to Shanghai. Thinking this way, it feels much closer. Why is that? The answer is simple. In daily life, the range of lengths you encounter is much greater than heights. Think about it. Tens of thousands of years ago, even without wheels, humans had already traveled distances of tens of thousands of kilometers, migrating from Africa to various continents around the globe. However, it wasn't until over 100 years ago, after the invention of airplanes, that humans flew to heights above tens of meters. Of course, even humans who can't fly can reach heights by climbing mountains. But even the height of Mount Everest is less than 9 kilometers. If you convert this height to length, your daily commute to work might be more than 9 kilometers. Jet airliners can fly at heights of 10 kilometers. Go up another 100 kilometers, and pilots become astronauts. At such distances from Earth, unimaginably large sizes are just beginning to appear. The distance from Earth to the Moon is about 378,000 kilometers, equivalent to 10 times the circumference of Earth. Venus is the closest planet to Earth, and the distance between them is over 100 times the distance from Earth to the Moon. Such sizes are beyond our imagination, becoming pure numbers. To understand them, we can borrow the method from the first part about understanding numbers. Fit it into your familiar scale. For anything beyond the human scale, you can take a similar approach. And then, for example, if Earth's size is about the size of a period in a standard font, then the distance to the Moon is about 15 millimeters, roughly the thickness of your finger.
And the sun's size is like a child's fist, located 6 meters away from this Earth period.
If we compressed the solar system to the size of a coin, then the entire Milky Way galaxy would be about half the size of China. At this point, you might have a bit of an idea about the scale of the universe. But actually, the Milky Way is just a small part of the local group, which has about 30 independent galaxies. Let's keep going. The local group is in turn a small part of the Virgo supercluster, which is about 100 billion times larger than the Milky Way and consists of hundreds or even thousands of galaxies. If you're not dizzy yet, imagine that there might be about 10 million superclusters in the universe containing billions or even trillions of galaxies. Given such vast numbers of galaxies, you should now understand why astronomers firmly believe that intelligent life beyond humans must exist in the universe. The enormity of the cosmos and the tininess of particles are equally astonishing. Even the largest superclusters in the universe are made up of fundamental matter, including atoms and subatomic particles, and possibly even smaller things. The smallest size the human eye can distinguish is about 0.1 millimeters, roughly equivalent to the diameter of a dust mite or a human egg cell or the thickness of a banknote. Although we can see a grain of salt or a tiny bug, humans still struggle to comprehend the microscopic world. The mechanisms of the microscopic world are completely different from the macroscopic world. This is because the way forces manifest in the two worlds is very different. There are only 4 fundamental forces in the universe: gravity, electromagnetic force, strong force, and weak force. Fundamentally, all the forces we experience in the macroscopic world, including tension, resistance, friction, and centrifugal force, are combinations of these 4 fundamental forces. For example, as a macroscopic being, you can breathe air and move through it effortlessly, but for tiny insects, air is a thick fluid made of countless molecules. Yeah. You think insects are flying? Actually, they feel like they're swimming. If we go further into the depths of the microscopic world, we have to learn some new rules. And rules that are hard to understand within the human scale. For instance, in the real world, when you clap your hands, you hear a crisp sound and feel the heat generated. But in the nanoscale world, or the even smaller picoscale that's 1/trillionth of a meter, atoms and molecules rarely collide. They just constantly attract or repel each other. And like tiny magnets, when one hand approaches the other, the molecules in your skin tense up and squeeze together, collectively pushing the other hand away.
This whole process happens quickly and at a microscopic level.
Similarly, you might feel your back against a chair or a car's bumper hitting a concrete wall. You think they're tightly pressed together, but actually, the molecules making up your body, the car, and the wall never truly touch. Everything you experience comes from electromagnetic forces. It's just that electromagnetic forces operate at such small scales we can't directly perceive them, so we mistakenly think our back is actually touching the chair. Beyond microscopic forces, humans also can't directly perceive the magnificent spectrum of light in nature. Now let's talk about the scale of light. Light comes in many forms. You've probably heard of visible light, infrared, ultraviolet, etc. What's the difference?
The answer is wavelength.
If light waves vibrate at low frequencies, we say they have long wavelengths and low frequencies, and vice versa for short wavelengths and high frequencies.
Visible light wavelengths range from about 380 to 750 nanometers, from red to violet. Gets the range humans can see.
If the light spectrum were a chopstick, visible light would take up less space than a speck of dust on it. Our eyes see rainbow edges gradually fading, as if dissolving into nothingness. But electronic devices can observe worlds far beyond red and violet. The universe is far more magical than we see. Since light speed is unbelievably fast, discussing wavelengths and frequencies forces us to confront extremely large and small numbers. Red light frequency is about 420 terahertz, meaning its electromagnetic field switches direction about 420 trillion times per second. If your car wheels spun that fast, you could cross the solar system in the blink of an eye. At this frequency, a single red light wave is about 700 nanometers long, roughly 1/10 the diameter of a red blood cell. Now, as wavelengths gradually shorten, red light becomes yellow, then green, then blue.
Finally, when wavelength shortens to about half of reds, it becomes violet.
As wavelengths continue shrinking, the spectrum enters ultraviolet range, invisible to us. X-rays and gamma rays fall within the ultraviolet range, and they have very wide applications in the medical field. What happens if we go the other direction, with wavelengths gradually lengthening? Microwaves are a type of longer wavelength infrared light. Your microwave oven uses microwaves, which get absorbed by specific molecules like water, fat, and sugar, making them vibrate, collide, and generate heat. But simultaneously, it passes through other molecules without any effect, like the dry outer surface of popcorn and potatoes. Many say microwaves heat from inside out, but that's actually a misconception. The real reason is food is usually moist inside but dry on the surface, so the interior heats first. Electromagnetic waves longer than microwaves are radio waves, used by radio stations and cell towers. Going further, electromagnetic waves have no length limit in the universe. But on Earth, where is the limit for low-frequency waves? You'd never guess. It's hidden in our brains. Human brainwaves can drop below 4 hertz. Dividing light speed by frequency shows such low-frequency waves have wavelengths nearing 100 million meters. These ultra-long delta waves occur in unconscious states. Ultraviolet has short wavelengths, high frequency, carrying high energy and penetration, damaging yet useful for non-surgical treatments like gamma knives.
Conversely, infrared has long wavelengths, low frequency, less penetration but strong heating effect, perfectly utilized by microwave ovens.
In daily life, UV and infrared each shine in their own ways. Light is electromagnetic waves, while sound is motion, specifically molecular movement through a medium. Our hearing is actually an extension of touch. Standing by loudspeakers, you often feel sound pressure on your skin. Bass rumbles like thunder. High notes pierce like needles. What you feel are pressure waves from colliding molecules. Ears detect these pressure changes acutely. Sound requires a medium, solid, gas, or liquid, to transmit energy. No medium, no sound. Some movies show spaceship passengers hearing sounds in space, but that's impossible. No matter how loud, sound can't travel beyond the atmosphere, since it can't propagate in vacuum. Of course, sound isn't exclusive to Earth's atmosphere. We bathe in the sun's radiation, but few consider how terrifying the noise from this giant fireball must be. If you've heard a crackling fire, imagine the sound from the sun, where gases and plasma of hydrogen, helium, oxygen, and metallic vapors burn at tens of millions of degrees. Only the void of space prevents these sounds from reaching Earth. However, scientists have detected the sun's sounds using instruments. Its vibrations are too low for human ears, but compressing 40 days of sound into seconds reveals strange bell-like tones, slow, resonant chimes. That's the sun's deep cosmic call. Like light, human hearing is extremely limited. We hear frequencies between 15 hertz and 20 kilohertz. Children easily detect 20 kilohertz waves, but this ability fades with age. By middle age, most can't hear above 15 or 16 kilohertz. Marketers exploit this difference. A UK security firm uses 17 kilohertz buzzers to deter loitering teens. Soon, people reversed this, setting phone ringtones to high frequencies. Thus, kids hear phones ringing while teachers and parents remain oblivious. Sounds above 20 kilohertz are ultrasound. Many animals hear better than humans. Dogs detect up to 45 kilohertz, cats hear higher, and bats emit calls exceeding 100 kilohertz. They use these calls for echolocation, while humans harness ultrasound for many purposes. Dentists use it for cleaning, doctors for non-invasive kidney stone removal, and engineers for material inspections. These applications use frequencies far beyond animal hearing, from 50 kilohertz to 18 megahertz. At the other end of the sound spectrum, when frequencies drop below 20 hertz, we enter the mysterious world of infrasound. Most marine mammals communicate using low-frequency infrasound because low tones travel farther. Humpback and blue whale songs range from 10 to 30 hertz, their deep songs carrying hundreds of kilometers. Remarkably, while humans can't hear infrasound, we can feel it.
A London research team once installed an infrasound cannon behind a concert hall.
While audiences enjoyed music, they intermittently introduced very subtle infrasound. Afterward, 22% of listeners reported intense discomfort or fear. Others felt precisely the opposite. They felt profoundly sacred and transcendent. Similar cases exist in daily life. Employees at a factory refuse to work in certain rooms because being there made them inexplicably uneasy. Later, they discovered cooling fans pumped not just air, but infrasound into those rooms. Some scientists now believe ghost stories originate from infrasound. The lowest frequency sound humans have detected comes from distant cosmic events. A black hole in the Perseus cluster, 250 million light-years away, emits sound waves billions of meters long. Specifically, researchers describe it as a flat, 57 octaves below middle C, lower than the deepest sound we can hear, quadrillions of times lower. Beyond frequency, volume and timbre are crucial dimensions of sound. Scientific principle: larger amplitude means louder amplitude. Larger amplitude means louder volume. Timbre actually comes from noise outside the standard spectrum. If a piano and swana produced identical pure tones without overtones, you couldn't tell them apart. But due to materials and shapes, their sounds aren't pure. They contain harmonics beyond the fundamental tone. These very overtones create the unique timbres of piano and swana. Beyond music, hot baths are equally pleasurable. Because heat signifies life, it's another vital scale in our universe. Heat's essence is kinetic energy, inevitably converting to motion that transfers between atoms until evenly distributed. We use temperature as a measure of heat, gauging how much energy an object contains. Nature's temperature range is vast. We're familiar with just a small segment, roughly from sub-zero temperatures of a few or tens of degrees up to flames of several hundred degrees. There are three common temperature scales: Celsius, Fahrenheit, and Kelvin. The first two are for daily life, Kelvin for scientific research. In Kelvin scale, each degree equals Celsius in size, but its zero starts much lower. As mentioned, heat's essence is motion. Faster atomic movement means higher temperature, slower means lower. But remember, at atomic level, nothing truly stops moving, meaning nothing in the universe is truly cold, just less hot. Thus, we define Kelvin zero as atomic motion cessation, absolute zero, approximately minus 273.15 degrees Celsius. Near absolute zero, atomic motion slows dramatically. If reached, no motion would exist. No light, heat, stars, galaxies, or humans. Good news. Absolute zero is unattainable. The coldest natural temperature is in Boomerang Nebula, gas from a dying star.
At approximately 1 Kelvin, minus 272.15 degrees Celsius. Lower temperatures exist only in labs.
Yet approaching absolute zero is nightmarish. Efforts to remove heat generate more heat. But it's worth pursuing. Astonishing phenomena hide in extreme cold. At ultra-low temperatures, atoms behave bizarrely, enabling unexpected tech advances. For example, materials like lead and carbon become superconductors. Superconductors, conduct electricity with zero resistance. Currents never decay in superconducting coils. Superconductors help scientists create exceptionally powerful and precise magnets. In a Japanese experiment, a maglev train using superconducting technology reached 581 kilometers per hour, breaking the world speed record for trains. And one day, entire power grids might use superconducting materials. The world near absolute zero holds incredible wonders. Looking to the other end of the temperature spectrum, the high-temperature world is equally astonishing. For most people, a candle flame provides ample warmth. But in the spectrum of heat, this is merely the starting point. Earth's core reaches over 6,000 Kelvin, Jupiter's core 20,000 Kelvin, while the Sun's core is about 15 million Kelvin. Many stars are hotter than the Sun, but 61 Kelvin is the upper limit. Exceeding this causes stellar collapse, exploding into spectacular supernovae. In 2010, scientists created 4 trillion Kelvin in a lab, breaking known temperature records. But temperature has a theoretical limit. Hotter particles move faster, nearing light speed while gaining mass. Continuous heating makes particles so dense they collapse into micro black holes, destroying nearly everything. This theoretical limit is about 1.4 times 10 to the 23rd Kelvin, including fundamental particles. In our universe, at least, this is the absolute maximum temperature.
Finally, the most mysterious scale, time, the greatest enigma in our cosmos.
All terms defining time, spring, summer, vacation, workday, are artificial and subjective. Time is entirely human defined. The only certainty about time is its connection to change. Without change, time ceases. Seconds, hours, years are all human scale constructs. We know these units well and use them to organize daily life. For individuals, the longest directly experienced time is a lifetime, less than a century. Compared to this, geological timescales are unimaginably vast. You might have seen time-lapse videos. Clouds move rapidly across the sky, their transformations condensed into mere seconds. Now imagine a time-lapse, where each frame represents 10,000 years. If filmed from Earth's birth, the final video would be 4 hours long. Human history wouldn't appear until the final second. This scale is what scientists call geological time. On human time scales, we must admit humans have recently severely impacted Earth's climate. But geologically, within Earth's 40,000-year climate cycles, we're likely entering a natural ice age. Global warming might delay it slightly. That's the ultra-long time scale. Now let's discuss extremely short times, when something happens lightning fast. We say in the blink of an eye, or like lightning, apt descriptions indeed. A blink takes about 1/3 of a second. Humans perceive events down to 1/10 of a second. It's faster than that, everything becomes a blur. If you flip a book of static images at 20 to 30 pages per second, the pages seamlessly connect. We believe we see motion. That's how movies work. The fastest observable times in daily life are milliseconds, thousandths of a second. A fly's wing flaps every 3 milliseconds. A basic camera shutter clicks in 1 millisecond. We can grasp milliseconds, 1,000 events per second. This is astounding, yet still comprehensible. But how to understand microseculus, millionths of a second? Consider a mouse click takes 500,000 microseconds, pushing human cognition to its edge. Yet beyond microseconds lie nanoseconds, picoseconds, femtoseconds. The deeper science goes, the smaller and more ignorant we realize we are. Across all cosmic scales, what we perceive is minuscule. But this doesn't mean we stop trying. Humans are part of this vast, complex cosmic spectrum. As long as we stay curious and bravely step out of the middle world to embrace broader scales, we'll gain more knowledge and unlock more secrets. Well, that's the scale of the universe. That concludes our interpretation of this book for you. You'll find the reading notes below the audio. We'll see you next time.